Hi, I'm Suzette for ALGOR. Today's show, Solving the Case of the Impact Force, is number 2 in ALGOR's Escape from the Past video series. A typical problem for the ancient Greeks was determining whether a stone beam, such as this one in the Parthenon, would hold up once the scaffolding was removed. Archimedes and others worked out formula to determine the size of stone beams for specified distances between columns, dimensions for scaffolding, and the structural members of the hoist they used to lift these giant stone beams into place. Roman engineers elaborated on this work, but the equations were lost during the Middle Ages. By the 19th century, engineering had advanced to the point where the success or failure of steel beams in modern structures could be predetermined. The technique was to calculate a value known as stress, which is nothing more than a force spread over an area, and then compare that value with the upper stress limit for the iron, which would be determined by stretching samples in a laboratory. First, the engineer would calculate a quantity known as the moment of inertia based on the cross-section geometry of the beam. The next step would be to calculate the stress using formula like this. By the late 20th century, a technique known as linear static, finite element stress analysis had been developed which enabled engineers to do similar calculations on real parts such as engine blocks, suspension springs, computer fans, and so on. An engineer would pull a model from a CAD solid modeling system into the finite element system, apply static loads, and get the stress results. All of this would be fine except for one thing. Typically, unless expensive experiments are done on laboratory prototypes, the loads are not well known. Also, in an assembly of parts, each part would have to be analyzed separately, with forces being transferred cumbersomely and inaccurately from one part to another. In today's example, we will consider the case of this simple steel bar. We are placing it on these stands. So that it becomes a simple beam with simple supports at each end. We will now propose to drop a 4-pound weight on this bar from a height of 1 inch. This example, though seemingly straightforward, will reflect the same principle as a child slamming into the retaining bar of a child seat, a car slamming into a foam pole, gears clashing together when a motor is turned on, or the impact when rail cars couple. So according to the handbook, the maximum stress on this beam will occur here, at the point where the force will be applied. Let's try the calculation as follows. The stress is equal to mc over I. M equals the torque applied, which is force times distance. C equals the distance from the center of the bar to the outer radius. And I equals the moment of inertia. Okay, for this bar, I equals 0.003068. And C equals the radius 1/4 inch. And M for this case equals the force times the length, or 23 inches divided by 4, or force times 5.75. Now let's do the force. The force would be 4 pounds if the weight were not moving. We are going to drop it from just 1 inch. Now we don't seem to know the force. Wait, let's use Hooke's law. Force is equal to the stiffness of the beam multiplied by the deflection. Okay, from the same handbook, we get this equation. The deflection equals the force multiplied by the length cubed and divided by 48 times the moment of inertia and Young's modulus. And solving for the force, we get F equals 48 EI over L cubed times the deflection. Now, the bar is made of steel, so Young's modulus is about 30 million. So the force equals 363.1 times the deflection. Uh-oh, now we don't know the deflection. Oh, maybe finite element analysis will work. First, we build the model. Now, the boundary conditions. The material properties. And finally, the force. Wait a minute. We still need the force. What if we balance the potential energy of the weight against the energy stored in the deflected shape? We might get into the ballpark that way, but we still need to consider the inertia of the bar as well as its change in potential energy. Anyhow, that's just not practical for things in general. The only thing left to try is a virtual experiment using ALGOR's AccuPack VE. We already have the finite element model. Now let's add in a second model for the weight, precisely 1 inch above the bar. And let's be sure gravity is right. Now we can start the model running. The monitor program is plotting the deflection versus time as we go. And we can see the step-by-step analysis happening here. At the end, we can make a replay of the motion, impact, and stress analysis in an AVI format and look at it with the Windows Media Player. Right here is the maximum stress in pounds per square inch. And here is the maximum deflection. Now, just for info, we can calculate the actual force. Plugging in the deflection, we get the force. See? The force is 56.6 pounds. Wow, that seems high. Let's check this out with an experiment. First, I'll use this ruler to check the 1 inch height. This piece of cardboard will serve as our telltale maximum deflection indicator. Now we'll release the weight. Let's see. We have about 0.16 inches deflection. About the same as the AccuPack VE event simulation run. So far, so good. Now, let's get the force. For that, we will reverse the experiment. May I have a volunteer from the audience? We will use the winch to pull up on the bar until the deflection is about the same. If we insert the scale in line between the cable and the bar, it will read the same force that it took to bend the bar when the weight dropped on it. Okay, in the bar. Okay, go ahead and take it up. We need to bend the bar 0.156 inches, which is between 1/8 and 3/16 of an inch. Okay, Jackie, let her crank. A little bit more? Good. Let's see what we have. The scale reads 56 pounds. Here's another question. Suppose the expected real-life design calls for a weight of only 1 pound dropping from 1 inch. What is the safety factor if we have designed using the 4-pound weight in our experiment? Some think that the safety factor would be 4, that the force would be 56.6 divided by 4, or 14.15 pounds. Let's rerun the virtual experiment with 1 pound instead of 4. Now the process is taking place. And the deflection is 0.0634. Plugging this into the equation for force, we get about 23 pounds. So the safety factor is only 2.46. Suppose the anticipated operating force is equivalent to dropping the 4-pound weight from 1 inch, just as we have done today. And we want to design in a safety factor of at least 4. From what height should we drop the weight and check the stresses? Let's do this case on the computer. We need to get a drop height such that the force is 4 times 56.6, or 226.4 pounds. Now let's raise the virtual 4-pound weight to 19 inches. And plugging in the deflection to get the force, 228.69 pounds, that's close enough. We need to drop the weight from 19 inches to get a safety factor of 4. AccuPack VE Mechanical Event Simulation for virtual prototyping from ALGOR. It's how engineering will be done in the 21st century.
Yeah, that's so good. Yeah.
There, thank you for holding that spine. I don't think they can.
One little chirping. Chirp this flow. Okay. Roll camera.
Roll cameras on.
And action.
Hi, I'm Suzette for ALGOR Incorporated. Today's episode is titled Escape from the Past, or Solving the Case of the Buckled Bar. Engineering began in the ancient world. Among the many creations of ancient engineering are 3 huge pyramids at Giza, Egypt, known as the 7th wonder of the ancient world. Their method of construction is today shrouded in mystery. Engineering methods advanced rapidly through the millennium. Culminating with today's method of computerized finite element stress analysis. Now, as we stand on the threshold of the 21st century, it's time to escape from the past. Let's consider this aluminum bar. We will run an experiment to see if ALGOR's AccuPack VE virtual engineering software can predict if the bar will hold up or fold up when a weight is placed on one end of the bar. We will use this mechanism, the Universal ALGOR Testing Machine. The bar is hinged at each end. By this hinge here at the bottom, and by this hinge in the carrier at the top. Note how the carrier, which can hold a variety of weights, slides along these vertical rods. In this experiment, we will have a weight on top of the bar. This weight will be held in place with this electromagnet. When we release the weight, it may cause the bar to buckle out to the side. The bar would impact this 2x4, which will serve as the floor. Let's now model the experiment using ALGOR's AccuPack VE to simulate this event and predict the maximum weight the bar can handle without buckling. Our plan is to see what will actually happen through animation on the computer screen. This "what you see is what you get" scenario is what we call virtual engineering. Then we will do the live experiment and compare the results with those predicted by the virtual simulation. We are starting out with roadmaps, ALGOR's Java-based, easy-to-use human interface. Now we select SuperDraw 3. SuperDraw 3's user-friendly features let us easily and quickly build this model. We simulate the effect of the hinges or joints using these small wedge elements. Using the FEA Add menu, we fix these nodes on the wedge and thus create a hinge. We constrain the top hinge to move along a vertical line, just like in the physical experiment. We do not know in advance which points on the bar will contact the floor. Therefore, in this case, as in many impact problems, the use of contact elements is not desired. What is needed is the ability for the points on the bar to contact the floor automatically. All the user has to do is put in the location of the floor. The software will automatically predict which parts of the bar will actually make contact with the floor. We will do 2 runs, one with 16 pounds of weight and one with 20 pounds of weight. Using ALGOR's new monitoring capability, we can see events unfolding on our computer screen as results are computed. After each run, we make a computer animation from the results. Here is the result of the run with 16 pounds in 1/4 time slow motion. Buckling is not predicted. And here is the results of the run with 20 pounds. It predicts several things. First, the bar is indeed buckling under the 20-pound weight. Second, a very large deformation has occurred. Third, the bar did contact the floor, which constrained it and forced it into its final shape. Let's further examine the significance of the floor. Without it, we still get buckling, but it is nothing like the correct simulation. Finally, modeling the removal of all the weight, we obtain the permanently deformed shape. Measuring the distance between the 2 ends with SuperView, we obtain 16.5 inches separating them in the permanently deformed condition. Let's go back to the experiment and see how well we predicted the event. First, we will use a 16-pound weight. Pressing the button releases the weight. Note that the bar supports the weight as predicted. Now the same test with the 20 pounds of weight. Again, pressing the button. Note that in fact, the column has indeed buckled as predicted. We do have a very large deformation. And the bar has contacted the floor, forcing it into the final shape. Let's do an instant replay in slow motion. As you can see, the AccuPack event simulation and the actual event match closely. Let's remove the bar from the apparatus so we can measure the permanent deformation. Observe how closely AccuPack VE predicted the permanent deformation. Predicting the event you just saw with the finite element system could be a formidable challenge. One of the more challenging aspects is predicting the contact and the subsequent separation between the bar and the floor. With AccuPack VE, however, all we had to do was build the model and specify the location of the floor. There was no need to put in special contact elements. Everything was automatic. The AccuPack VE event simulation, the actual event, the case solved. Virtual engineering and automatic contact from ALGOR for engineering in the 21st century.
We are showing how ALGOR software predicts fluid flow interacting with the structure. We will use this 12-volt computer chip fan to show how ALGOR can optimize its design. Notice the rib that houses the wires is wider than the other two ribs. Those are thinner because they thought it might be a better design. Let's begin the experiment. The fan and the housing are rigid. The fan is rotating at 300 RPM. We are using smoke to dramatize the airflow. Notice the flow pattern near the narrow ribs. Now, let's go to the computer to see if ALGOR can make the design better. The finite element model of the blade and housing was made in ALGOR SuperDraw. The real fan was photographed with a digital camera to produce a bitmap. The engineer used a tracing function in SuperDraw to construct the blade geometry of the model. SuperDraw needs only a few mouse clicks to create the mesh around the blades. Next, a surface mesh of the remaining volume was automatically generated and fitted to the previously created mesh. ALGOR Hexagon made the 8-node brick mesh connecting the blades and support. ALGOR's control software, Eagle, coordinated the changes in the geometry, the moving boundary conditions, the fluid flow analysis, and the animated visualizations to predict the airflow through the fan. Let's view the animation of the airflow over time. The flow pattern changes dramatically when a blade passes over one of the two narrow ribs. The first narrow rib stirs up turbulence, which is made worse by the second rib. The wide rib tends to smooth and straighten the airflow. Turbulence generated by the narrow ribs blocks airflow in 1/3 of the fan. So, using ALGOR software to optimize the design, the manufacturer could increase the flow rate, reduce the power requirements, or make a smaller fan. This historic oil can was made by the Pittsburgh Manufacturing Company. I will use it to show the principle of snap-through buckling and how ALGOR's AccuPack nonlinear software can readily analyze and predict this effect. Let's take a closer look at the oil can. Note, as I press on the bottom of the can, the movement seems linear at first. But as I press harder, there's a sudden snap, and a relatively large displacement occurs in a sudden jump. Then, when I release the pressure, it suddenly snaps back. To determine the thickness of the bottom, we purchased 2 identical oil cans and cut out the bottom of one. We measured the thickness at 10,000ths of an inch, or approximately 1/4 of a millimeter. We began the analysis by building a 2D finite element model using ALGOR SuperDraw. The critical part was modeling the spherical shape of the bottom of the can. Note that the edges are fixed to resemble the way the bottom is attached to the real can. A force of 1 pound was applied at the center of the computer model, ramping it up over time to simulate the real action of pressing the bottom of the oil can with your thumb. The applied force curve versus time looks like this. Here is a graph of the displacement of the center node versus time. The graph is automatically generated by the software during the run. Note the sudden plunge of displacement at the moment of snap-through. And here as the bottom snaps back. The sound or pitch of the snap-through agrees with the frequency shown on the plot. It occurs at 198 cycles per second or hertz and corresponds to the note G below middle C. The pitch of the snapback is somewhat higher with a frequency of 396 hertz, or the note G above middle C. Let's take a look at the animation of the results. The animation shows the actual response of the model to the input load curve. The animation is, of course, in slow motion, with the actual response taking only 1 second. ALGOR AccuPack has the power and stability to handle snap-through buckling. It can make solving your problems a snap through. Many FEA analysis packages cannot predict the effects of load stiffening when attempting to avoid potentially destructive responses to vibration. Load stiffening occurs when an object, such as this guitar string, is stretched to produce a specific frequency or tone. For example, as I loosen or tighten the string, its tone or natural frequencies will change. In an airplane or car, loads or forces, and therefore natural frequencies are constantly changing. Therefore, to predict the dynamic response, you must consider load stiffening. ALGOR offers 2 ways to predict frequencies as a result of load stiffening. The first way is with the vibration level 2 extender. First, we measure the force applied to produce this low A note, or a natural frequency of 110 cycles per second, or hertz. Multiplying the measured force with a leverage factor of 220 for the screw gives us an applied tension of 31 pounds. Then we measure and weigh the string to obtain its mass density. Also, we need to measure the cross-section area of the part of the string which will be in tension. Now we can plug the data we have gathered into the load stiffening module, which predicts the first vibration mode at 110 hertz. The correct result. Note that the second mode is 1 musical octave higher at 220 hertz, and so on up the musical scale. AccuPack Nonlinear Analysis Extender is the second way to predict frequencies as a result of load stiffening. Note that when the A string is twanged, complicated waveforms appear. Notice that there appears to be waves within the wave of the string, and that the outer envelope of the mode shape itself seems to have waves. These waveforms result from the base frequency combining with the other frequencies within the string. For the AccuPack analysis, we will twang the string at a typical spot which would occur during actual playing. Notice the tension force and the boundary conditions. Looking at a plot of the position of the center node versus time, we can get the base frequency by counting the peaks. Here we have approximately 11 peaks over 0.1 second, or 110 hertz, which agrees with the previous calculation. Note the higher frequencies coming in here, and lower frequencies, or beating, showing up in the waveform envelope. Beating is often responsible for the low frequency growling sounds you sometimes hear in airplane cabins. Plotting the node which was twanged, the higher frequencies are even more evident. Counting the largest and second largest peaks together, we get the second octave 220 hertz, and so on up the musical scale. Finally, let's look at the visual response of the string as predicted by AccuPack. It is this complicated response that causes a simple string to produce a rich tone. You need software that can predict the effect of load stiffening so that your designs can produce music to your ears.